Now I want to talk about subdivision on chain groups. So one of the basic points about barycentric subdivision is that the homology of K prime is going to turn out to be isomorphic to the homology of K. And that's a key ingredient in the fact that homology is invariant under homotopy equivalence. So we need to prove that. In order to prove that, we need to show how to relate the chain group C star K to the chain group C star K prime. So we'll begin this discussion with kind of an example. So here's our complex K that we discussed earlier when we introduced subdivision in the first place. And here's one generator of the group C2K, is the simplex ABD. Right? We've indicated it in the usual way with a little circulating arrow to show that it's we're looking at the generator ABD, which is the same as BDA or DAB, but is equal to minus ADB, for example. Okay. And so we want to have a chain map gamma from C star K to C star K prime. So that's got to send this generator ABD to some 2 chain over here. And it's kind of clear which 2 chain we want. We just want to take all the triangles that kind of cover the same space as ABD does. Okay, so there are 6 of those triangles. I've written them here. First one, we've written a 1 here. That's for this A hat, AB hat, ABD hat. And 4 here, for example, that's for this, that's got B hat, BD hat, ABD hat. So 6 of them all together. And so the plan is going to be that gamma ABD should be the sum of all these 6 things, at least up to a plus or minus sign. So how should the signs be determined? Okay, well, this guy is all anti-clockwise, and so what we want is to take all of these guys anti-clockwise. Okay, that's how it's supposed to work. And but notice if we if we look at theta 1, then that just kind of naturally occurs anti-clockwise. We've got A hat, AB hat, ABD hat, and if we see that's kind of going around here in an anti-clockwise way. But if instead we look at theta 3, so we've these thetas, we've kind of listed them in the obvious sort of systematic way. There's barycenter of a 0 simplex, then of a 1 simplex, then of a 2 simplex. Okay, but if we do that for theta 3, then we find that we've got beta hat, B hat, AB hat, ABD hat going around in a clockwise direction. So we need to put in a minus sign against the theta 3 in order to turn it around so as it goes anti-clockwise like everything else. Okay. So the so what we want is to have gamma ABD. We should have theta 1 with a plus sign, theta 2 with a minus sign, because if we just do theta 2 in the obvious way, A hat, AD hat, ABD hat, that's clockwise, so we have to put in a minus sign to make it anti-clockwise. Similarly, theta 3 has to be with minus, theta 4 has to be plus, theta 5 has to be plus, theta 6 has to be minus. Okay, so that's easy enough to kind of just read off from the pictures, but that's only for the kind of 2-dimensional case. We need to understand kind of what's the general rule, which we can interpret in higher dimensions for whether we need plus signs or minus signs. And the way it goes is like this. So if we look at this theta 5, so what we've got D, and then AD, and then ABD. So we start off by introducing D, then we put in the A, then we put in the B. Okay, so we introduce them D, then A, then B. As opposed to here, we had ABD as our original thing. So DAB, that's an even permutation of ABD, right? You just cycle the D round to the back. That's a 3 cycle, which is even. So you get a sign of +1 for that. Whereas you look at theta 6, okay, here, so we got D, then BD, then ABD. So we introduce D first, then we introduce B, then we introduce A. Okay, so DBA is an odd permutation of ABD, right? It's just swapping the A and the D around and leaving the B in the middle on its own, so it's a transposition. Odd permutation, the sign of that permutation is -1. So the way the rule works out is that in that case we have to put in a minus sign. So so we get 3 even permutations of ABD and 3 odd permutations. That's giving us 3 pluses and 3 minuses in this formula for gamma ABD. Okay, so here's the general definition. We've got a simplex sigma, V0 up to VD of K. And we've got any permutation pi of 0 up to d, then we're going to let phi sigma semicolon pi to be the simplex tor naught hat up to tor d hat, where tor I is v pi of naught up to v pi of I. Okay, so that's tor I, and then tor I plus 1 would be the same, except you put v pi I plus 1 on the end, so that's tor I is contained in tor I plus 1. So yeah, we've got this chain of simplices, tor naught, tor 1 up to tor d, all nested one in each other. So the corresponding tor naught hat up to tor d hat, that's a simplex of k prime. Remember, that's the rule for simplices in k prime. If you've got a chain of nested simplices in k, then their barycenters form a simplex of k prime. Okay, so that's our phi sigma pi, that's a simplex of k prime. And gamma sigma, we take the sum of all these guys, phi sigma pi, we take the sum over all possible permutations, and we multiply by the signature of the permutation pi. And that gives us an element of, that gives us a D chain in K prime. So the key point is that this is actually a chain map. In other words, D gamma is gamma D. Okay. So let's give at least a partial proof of that. Okay. So the claim is that for any simplex sigma of V0 up to Vd, as we had up here, that D gamma sigma is the same as gamma D sigma. And we're just going to do the case D equals 2. So again, we need some kind of abbreviated notation for this. So as we've done previously, for the simplex V0, V2, or the corresponding chain, we're just going to write 0, 2. But what about simplices in K prime? So a typical example is like this. You've got the 1 hat, then 0, 1 hat, then 0, 1, 2 hat. Okay, so I'm going to write that, simplify it down, slim it down with bars. So we've got 1, and then a bar here, and then 0, 1 for this 0, 1 hat, and then a bar, then a 0, 1, 2 hat for the last thing. Okay, so what's gamma 0, 1? Okay, so you have to do this, follow this kind of prescription up here. You get 2 terms, there's 2 permutations of 0, 1. So here, this is one where we introduce the 0 first and then the 1. This is where we introduce the 1 first and then the 0. Introduce 0 first and then 1, that's just the identity permutation, the plus. Introduce the 1 first and then 0, that's the permutation which exchanges 0 and 1. That's an odd permutation, so we get a minus. So gamma 0, 1, 0 bar 0, 1 minus 1 bar 0, 1. Gamma 0, 2 works the same sort of way. You get 0 bar 0, 2 minus 2 bar 0, 2. And similarly for gamma 1, 2. So now remember our D sigma. So our sigma was 0, 1, 2. D sigma, you get omit the 0 to get 1, 2. Omit the 1, you get 0, 2. Omit the 2, you get 0, 1. With alternating signs. So gamma 1, 2 minus. So here D sigma is 1, 2 minus 0, 2 plus 0, 1. And we want gamma D sigma, so we have to apply gamma to that. Okay. So gamma is just it's a homomorphism, so we get gamma of 1, 2, which was this 1, 1, 2 minus 2, 1, 2 here. And then you get minus gamma 0, 2. And then gamma 0, 2 is the 0 bar 0, 2 minus 2 bar 0, 2 here. And then you get plus gamma 0, 1, which is 0 bar 0, 1 minus 1 bar 0, 1. Okay. Okay, so then we just tidy this up a little bit. There's actually not any cancellation going on here. The only thing we really need to do is to say we've got a minus 0 bar 0, 2, and then you get a minus and a minus, so that becomes plus 2 bar 0, 2 there. And everything's the same. Okay, so that's our gamma D sigma. Okay. So then we need gamma sigma. So remember gamma sigma, we've got to have term for every permutation of 0, 1, 2. There's going to be 6 terms. And here's the one for the identity. We introduce the 0 first, then the 1, then the 2. And here we introduce the 0 first, then the 2, then the 1. Here introduce 1 first, then 0, then 2. 1 first, then 2, then 0. Here 2 first, then 0, then 1. 2 first, then 1, then 0. Okay. So you get 6 terms, and that gives us our gamma sigma, which is 2 chain is in C2 of K prime. Okay, so now that's our gamma sigma, and then we need to do D gamma sigma. We're supposed to be proving that D gamma sigma is the same as gamma D sigma. So for each of these things, we have to take each of these 6 terms, we have to apply d to it. And so we take d of this, we omit the 0, we get 0, 1 bar 0, 1, 2 here. Omit the 0, 1, you get 0 bar 0, 1, 2, which is here. Omit the 0, 1, 2, you get 0 bar 0, 1, which is there. Okay, and so yeah, so we get 3 terms in d of this, which we've written as a column in this little table here. 3 terms for d of this in that column. 3 terms for d of this in this column. 3 terms for d of this in this column, and so on. Okay, so now we've got 18 terms. But there's a lot of cancellation goes on here. So let's see how things cancel. Here it's this term here, 0, 1 bar 0, 1, 2, cancels with this minus 0, 1 bar 0, 1, 2. Is minus 0, 2 bar 0, 1, 2, and a plus there. And a plus 1, 2, 0, 1, 2, minus 1, 2 bar 0, 1, 2. So we find that everything on this first line cancels out. Similarly, on the second line, everything here cancels out. This is basically what you're seeing here is just if you draw the subdivided 2 simplex, you've got the edges around the edge of the triangle which don't get cancelled, but then you also get the edges on the internal edges cutting through the triangle, and they all cancel out. We've seen that kind of cancellation before. And then if we look at this last line, well, you've got 0 bar 0, 1 minus 0 bar 0, 2, etc. 6 terms here. And you just check through them all, you'll find that exactly what you've got is the same as this gamma d sigma, which is written across there. Your 0 bar 0, 1 is there, minus 0 bar 0, 2 is there, minus 1 bar 0, 1 is there, and so on. Okay, so we find that gamma d sigma is the same as d gamma sigma as promised.